Struthers, who's going to be talking to us about reimagining the NHS dashboards and open source approach with Plotly Dash. While she's getting in position, can I remind you all, if you haven't already checked in, please do so with the QR codes that you'll see dotted about the place. And also pop back in the foyer and collect your raffle ticket for a lovely NHSR mug. Thank you very much. Take it away, Jennifer.
Okay. Hi everyone, my name's Jennifer Struthers. I'm a data scientist with NHS England. I'm a former member of the RAP team there, and I'm currently working in quality and improvements to help automate some of their analytical processes. But a few months ago, I undertook a project to reimagine the maternity services data and do an experiment in open source dashboarding. Because as a member of the RAP team, I felt like a lot of my work was getting a bit reproducible, and I wasn't really expanding my skill set, and I wasn't really learning much new. So I signed up for the ONS Data Visualization Accelerator Scheme, where you propose a project, and then if it gets accepted, you get a day off a week to enact that project. And so I was looking around, and then that's when I came across this. This is the current maternity services dashboard, and when I first saw this, I just felt a bit overwhelmed. Like, there's a lot of information on it. Here you've got the breakdown for Airedale Trust. It's the age of mother at booking. You've got it broken down. There's a time series. Then you've got that information for all trusts in an alphabetical order. And it just felt a bit overwhelming, like as a layperson who's not very familiar with this data. But maternity services is something that affects us all, or affects who people we love. And so I felt like this should be something a bit more open and accessible. I'm currently living in Leeds, and so if I wanted to find out this information for Leeds and look down this list of all trusts, I'd scroll down to Leeds, find that at L, and then I'd think, what's nearby? Like, it's probably York, I guess. So I'd scroll down to York and like, okay, and then I want to compare. I've got to flick up, down the two. But maybe there's something in between that I don't know about. I don't have an encyclopedic knowledge of all the healthcare providers in the Leeds area quite yet. And so I thought this would be much better done in like a more visual manner, like a map. And so I decided that this would be my project. I would reimagine this dashboard, but have it a bit more visual, a bit more accessible, and also do it in an open source manner. This, like a lot of our dashboards at NHS, is built in Power BI, which is a Microsoft product, which means that we're locked in to using that. And if the prices go up, then we just have to pay them. And so I thought, okay, I will try and do this in a way that's going to be completely free. And so that's when I found Plotly Dash. And Plotly Dash was going to be the tool that I could use in order to build my open source dashboard. So some pros of it, it's open source, which I'm sure we all love here, which means that there's a huge community around it. People post their code online, and it's completely open, completely free to use. It's fully customizable, so I can do anything that I can think of doing in it. It's not restricted to someone that at Microsoft thinks they know what I want to do. I just have to be able to build it. It integrates really well with Python libraries, so I knew I'd need to use stuff like NumPy, Pandas, etc. Integrates really well with that, and also, importantly, you can build in interactive elements. I wanted people to be able to click into my dashboard and have it react to what they were doing. But some downsides, I found that it required, I would say, at least intermediate to advanced Python skills in order to do anything more than just like a simple dashboard. Quite a bit of manual setup for it. There's no one button and then it's in front of you, and there's no built-in data management. You have to do all that yourself in the background. But I had my idea and I had my tools, so I was ready to go. And that's when I had to think about how I was going to build it. There's a lot of data there, and there's a lot of things I can get out of it. And so I used the thin slice development strategy. If anyone's worked in a RAP manner, you might be familiar with this. There's a link at the bottom if you want to find out more. But imagine your entire output, your entire dashboard is this pizza. All I want is the thinnest slice of it. I just want to go from the start and to the end just for a singular output. And so that way I can find all the tricky bits along the middle, figure out how to fix them without being overwhelmed about the amount of things I have to do. So I chose my singular output to be a map of the regions of England showing the rate of babies born per 1,000 people, and this was the data that I had. You can see here it's just value, it's not actual rate, so I had to go and then find the population for that area of England at that time and do some magic in order to manipulate that, join it together, get the rate, use geopandas to get it put on a map. But after a lot of effort, I got this, which was my thin slice output. And so this is the rate of babies born per 1,000 people for 2022 to 2023, which is the most up-to-date version of the data that we have currently. And you see here something quite interesting is that London, so I thought, yeah, London, of course, it's got more babies born, more people live there, but it's actually got a higher rate of babies born. Everywhere else is kind of the same. They're all about that like 8-ish per 1,000 people mark, except for London and, interestingly, the southwest, which is much, much lower compared to the rest of the country, which I thought was really interesting to see visualised like that. Now I had that, I had to move on and get like another quick win. So what can I do to get a quick win? Well, that's the regions. We have all this data in that data set for the providers. So I'll just do that. And because I worked in a way of using functions in a reproducible manner, there was only a few things I had to tweak, and then I had my map for the providers. This is the number of babies born per provider, so not rates, because I couldn't get the population for each individual provider. But you can see there, and these are just images, but you could click on to each of those dots and find out the name and the actual number for each of them. And in the highly populated areas, you can zoom in where there's lots of providers. I needed to expand my thin slice even further. So now I had my maps, but I thought, well, I could probably show this data in like more ways. And so very easily, I just built a chart. This is the same information as before. It's just presented in a slightly different format for anyone who's interested in that way. So, okay, I wonder if there's another way that I can present this data. It's like, well, I've got it for a couple of years, not that many, but a couple. And so I'll just build a time series. And I found this really, really interesting as well. This is only 3 years, so it's maybe not indicative of a trend just yet. The next year comes out maybe December, so it'll be interesting to see what happens there. But there's this bump in the middle for 21-22, and my hypothesis is that that's actually the COVID baby bump. So all the COVID babies would be born in that financial year. And so I'm really curious to see if there's like a complete downwards trend to see if the babies born this year will actually like completely be less than 2020, 2021. But just something I really thought was interesting, showing the data in this way. I kept going out. There was lots more metrics. It wasn't just the number of babies born. There was one that was the age of the mother at booking, which I showed at the beginning. And so I turned that into the percentage of mothers over the age of 35 for that year, because I couldn't, on just a map, show the breakdown of that data. And so you can see there, again, London's got significantly older mothers at the time of booking than the rest of the country. But it was really important to still have the breakdown of that data, so you could just transfer that into that chart, and you can see that the red crosses there indicate the comparison to the average. And again, of course, that same data in the time series like before. Again, a really interesting trend of the green and the orange line like switching over, so it'll be interesting to see if that carries on into the next year. And working in this reproducible way means that these charts are just carried across for every single region, every single provider. You just have to click and you will see the data for that region. So I spent, it was about 3 months I spent, like 1 day a week learning this, and I took away like quite a few things from it. First one is that maps are quite fun. I really enjoyed seeing the data visualized in this way, but they're not always the best way to show data. So there's these two ones I've got here. The one on top is for the smoking status of mothers, so this is quite easy. It's like a yes or no question. So very easy to see the percentage of smokings at booking. But then the one at the bottom is for the ethnic category of the mother. And that was a bit more complicated because I was thinking, what kind of story am I wanting to tell? Like, I don't think I want to present a map of, well, here's the percentage of white mothers in Britain in this region. It felt a bit overly complicated for what I was wanting to do. So I had to consider how I wanted to present the data. And the data could just be seen in this chart, and I could just leave the map blank, which is what I chose to do for that, because this was more an experimental project. Setting up a dashboard from scratch is a lot of work. I can see why people do it in Power BI, where it's all a lot of it's done for you. I had a lot of Python skills before, but I certainly learned a lot, and I could see how it's really intimidating for a team to be thrown into that. And linked to that is bugs on bugs on bugs. It felt like every single thing I did was just introducing a new error or a new complication, especially with the interactivity between the maps and the charts. And so it was quite difficult to get stuff going. And I also learned that nothing is truly free forever, which is why working with open source tools is so important. I really wanted to get my dashboard up online so I could send people a link and be like, here's the work that I've done, here's what you click around, try it. But it was so difficult to find a free platform that would do that for me. I found a singular one because there's many articles out there saying like, try this, it's got a free tier, try this, it's got a free tier. But those articles were 1 year old, and by the time I'd read them, the free tier had been sunsetted, which was probably their business plan from the start. So I did find one, and so here's some links. The code is, of course, up online for anyone to go try. You can find it just at the NHS England, and you can fork it, try it. There's a live site. The issue with that free tier is that, one, it's extremely slow. So if you click on it and try to interact with it, you've got to give it a few seconds because it's hosted. I think it's 0.1 CPU, so it's very slow. But if you host it locally yourself from the code, I promise it's a lot nicer. And also, it's only up for 15 minutes at a time. So if no one clicks on it in 15 minutes, it goes down. I have to spin it back up. So when I come down, I'll spin it back up and I'll post it on the Slack so anyone can go and click around for the next 15 minutes. If anyone wants to find out anything more, I've also put my email up here. If you want to contact, get those links, anything like that. But yeah, thank you.
Thank you very much indeed for that. There are quite a few questions for you on the Slack channel, so we probably won't have time to get through them all before the next speaker. And can I ask Scarlett Kynoch to make her way up towards the front whilst we're asking the questions? So, first question, can you tell us why you chose Plotly Dash versus an alternative?
Yeah, so one of the main alternatives out there was Streamlit, and it was actually just a convenience of the time working on company laptop. There are certain restrictions in place, and Streamlit at the time was actually blocked. And so Plotly Dash was my main alternative. I also had a mentor on the project who worked in the cabinet office because it was part of the scheme that you were linked up with someone a bit more experienced. And Plotly Dash was something that he had used in the past. And so it was a bit more of a convenience thing. I couldn't use the main alternative, and my mentor had experience with it. That was the main reason.
And have you had feedback from your stakeholders who used the original Power BI dashboard?
Yes, so I reached out to the maternity team in order to show them what I'd done, because I'd reached out to them before to ask if this would be something that would be useful to them, if they'd be interesting, and they gave me a bit of information, told me that their dashboard is actually, it's not really intended for the public, hence why I was probably finding it a bit like, ugh. And it's more meant for people within the field, and so they thought it'd be really interesting to see what I could do. So I presented it back to them, and they said that they really loved the visual aspect of it, and so they were committed to adding a map for the next one. Still in Power BI, unfortunately, because none of them really had the tech skills to kind of introduce something like that at once. But they were really interested in playing about with it themselves, learning how to use Git so they could access the code. Yeah.
Fantastic. Right, so thank you, Jennifer.
Thank you.
If you would like to head over to the Slack channel and have a look at the other questions there, I'm sure there are lots of people who would be really interested in hearing further from you. And next, can we welcome to the stage Scarlett Kynoch, who's going to be presenting on using machine learning and secondary care activity data to identify risk of cancer earlier.
Thank you very much. Okay. Oh, that's not the slide. Well, while that's being sorted, I'll just introduce myself. So I'm Scarlett Kynoch, and I am a data scientist in the central data science team, but I'm actually currently undergoing a placement in the National Disease Registration Service. This was a project that I helped with just before I left the central data science team. And yeah, this is going to be about using machine learning models on secondary care activity data for early stage diagnosis of cancer. So just to give a little bit of a background on this project, this was a collaboration with the strategic analysis team and the central data science team. Our key stakeholder was the NHS England Cancer Programme, and they report directly to the National Clinical Director for Cancer. So the situation that we were looking at is there's an NHS long-term goal, and the aim is to increase early-stage cancer diagnosis by 2028. This is due to the impact that this has from late-stage cancer diagnoses. So this is due to patient outcomes and also just the effect on mortality and survival rates. We recognised within the team that we had a skill set that could apply these novel machine learning methods to predict the risk for these patients, but also as NHS England, we had the ability to create a patient-linked data set as well to apply this to. So we worked with our key stakeholders to identify our main objective. This was to identify characteristics of cohorts of patients who have a more increased risk of developing specific types of cancer, and this would be within months and years of their diagnosis. So we focused on 9 priority cancers. These were outlined because they had a lack of screening programs and also tended to have a higher cancer incidence at later stages. So I'm just going to give you an overview of the code base that we have. So we actually have 2 repositories for this code. One of the repositories is hosted in the National Data Platform, and this is where we do all of our data engineering and also our feature engineering. And this is where we link all of the data to create a pseudonymized patient-linked data set. The other repository is where we do all of our data analysis. So this is actually done in UDAO. And in this repository, we do all the descriptive statistics, train our models, and then get out the insights from these models. Now, both these code bases is written in Python. We also use Git for version control, and we're also hopefully trying to publish our code on GitHub, but it's not quite there yet. We're doing the data engineering one first, and hopefully that will be happening soon. So I'm just going to give you an overview of what the data engineering repository does and how we create this patient-linked data set. So for our patient-linked data set, we actually combined 7 data sets that we had access to. We used the master patient index data and the bridges to health segmentation data to get out our demographic and socioeconomical variables. So demographic being gender and age, and socioeconomical variables being levels of deprivation, as well as something called ACORN household type, which is a definition of your household that you live in. For diagnoses, we use secondary usage services, inpatient and outpatient appointment data, as well as emergency care data as well. So the kind of diagnoses that we got out of this is whether individuals like comorbidities, so this is like heart disease, as well as like diabetes, for example. And then also for our specific cancer types as well. So we use ICD-10 codes to derive these. Also within this data, we got our interactions with the healthcare system as well. So this included like the total number of counts in the last year and the last 2 years, and etc. And then also we had access to 111 call data. So with this data, we actually had like symptoms that have been reported by individuals for 111 calls. And we worked with clinicians to actually ensure that the 111 call symptom reported data that we got was actually relevant to the cancers that we were looking at. So we got specific features out, and that's just due to how vast the data set is. So to just make sure our features are more specific. And also within this, we also got out the interactions as well. So the total number of counts as well. We also had access to ONS mortality data, and this was to essentially help with our exclusion criteria. So part of our exclusion criteria is that we exclude individuals that have died before a cutoff date, which I'll explain on the next slide, and also remove individuals that have died after the cutoff date if it's for any other related disease that's not cancer. So just to give you a little bit of a flavour of kind of what this data looks like, and I've just picked very specific examples here. We have the cut-off date for August 2021. This is partly due to the limitation with the Bridges to Health segmentation data, because we only have this up to August 2021. But for like secondary use as an emergency care data set, we have like a larger range, which is why we can get that cancer of next diagnosis after that point. It's worth noting that with the cancer diagnosis, we only look at primary cancer diagnoses and also an early stage as well. So how we kind of derive this is we look for previous cancer diagnoses in the previous 5 years. So there's a slight limitation there because we only have access to the data for those previous 5 years, but that's what that metric is representing. In terms of 111 calls, this data actually only goes back to April 2018, so we can only go back to get those sort of like last 52 weeks up to that time point. But as I explained with the secondary uses service data set, we get out those sort of diagnoses and comorbidities, and we use ICD-10 codes to derive these categories. So for example, the other disease of urinary system in the last 260 weeks is derived from that. Okay, I'm now going to give an overview of how we do our data analysis. So in our overall data set, we end up with about 24 million individuals in our data. Part of the reason this is a little bit smaller as well than expected for the general population is we also have an exclusion criteria of filtering down to the ages of 40 to 74. We split this data set into a train, test, and validation split. So this is a 60%, 20%, and 20% split. And then the next thing we do with our training data is we actually create an undersampled training data set. And the reason we do this is we want to balance our cancer and non-cancer cases to ensure that we don't have a class imbalance when we're training our model. So to give a bit of an idea of how we do this, so for example, in the case of bladder cancer, if in this 14.5 million we have 3,500 cases for bladder cancer, we'll bring all of those cases forward. And then on the remaining cases which they have not been diagnosed with bladder cancer, we will then do a sampling, and we use Spark to do this. Part of the reason we use Spark is because obviously the data set's huge and Spark is more computationally efficient. So we use the sampling method of that and setting a random seed to ensure that this is reproducible. This results in, for this case, an undersampled training data of about 7,000 individuals. Once we have this trained undersampled data set, we can then train our machine learning model. So the machine learning model that we use for this is called Spark XGB classifier. We also explored some other models. So we explored linear support vector classification, a random forest classifier, and then the traditional logistic regression as well. By following this process that I'm going to talk you through now, this one ended up being the one that performed the best. So this was the one that we took forward for all of our models. So to give a bit of context, Spark's XGB classifier is a type of XGBoost model, but it's supported by Spark. So we use a package called HyperOpt to essentially define our feature space. Feature space being the hyperparameters that essentially like configure your model. What's quite interesting about this is we can use something like, for example, hp.log uniform, which actually allows you to sample your range from a lower end. So you can sort of use it. There's like they've got different like uniform and sampling to sort of help encourage these ranges. Once we've used the parameters to then configure the model, we then use that undersampled trained data set to train the model, and then we actually use the validation data set to get out our metrics from how that model is performed. Now, bearing in mind this validation data set does have a class imbalance, so it will have a smaller bladder cancer compared to the general population that do not have bladder cancer, so it's a larger population we're validating on. Now, the metric we used to essentially identify the best model with the best parameters is something called area under the curve. This essentially is a trade-off between your true positive rate and your false positive rate. True positive being the number of correctly diagnosed individuals, and that has also been identified by the model. And then false positive rate being where the model has decided that someone has bladder cancer, but actually they've not gone on to develop it. So in this case, what you would want is 0.5 is the random classifier. So you would want it to be more towards your 1, which is your perfect classifier. So we were trying to maximize this with the parameters off of our trained data set. Now, we track all of this using something called MLflow, and that allows us to then work out what our best parameters are from the area under the curve that we have derived. So once we've done this for all of the 9 specific priority cancers that I spoke about, we then also have a test data set, and this is where we get our model evaluation. So this essentially is a data set that's been unseen by the model. And these are currently the results that we have for each of those 9 priority cancers that I showed you. As you can see, it ranges from, for area under the curve, it ranges from 0.69 to 0.83, the lowest being 0.69 for ovarian cancer, and the highest being 0.83 for esophageal cancer. But I'm just going to continue with the bladder cancer example to explain how we can use these trained models to then extract out insights from them. So, essentially, going back to our main objective, we wanted to identify characteristics from high-risk cohorts. To identify these high-risk cohorts, we decided to use a methodology called a lift curve. So how this works is you take your trained model, and for each of your trained model, it will give a risk prediction score for each of your patients, depending on the features that has been obviously reported in the data set. And then what you try to do is there's essentially risk thresholds. So going from the, I believe it would be your right towards the left of the curve, you then increase the risk score that you'd be looking at. So for example, we've got here the 0.8, and then this will increase 0.85, 0.9. And what this ends up producing is you end up looking in a smaller cohort of your population, but it has a higher cancer incidence. So it then produces these sort of high-risk cohorts. To sort of put that into perspective, for the general population for bladder cancer, it's 1 in 4,060 in our population. And as you increase it to, say, the 0.95 threshold, this increases to 1 in 123, which is approximately about 33 times higher. Now, once we've identified these high-risk cohorts, we can then use that model to extract out the key features that have been reported from those high-risk cohorts. And what we actually found is blood in urine 111 calls and also the pain or frequency of passing urine ended up being one of our top features. And actually, these are actually in NICE guidelines and reported for bladder cancer, so that was a really good sign to see from the model. Additionally, we spoke with a clinical fellow as well, and he did raise that, like, for example, COPD, which is on there, has been shown to have association with bladder cancer as well. So this was really positive to see from the results that we've got so far. Now, this whole thing we've kind of been talking about is sort of case finding. So there are definitely other approaches to this methodology that you could do. You could look at the features that are being extracted out from your model and start combining those highest features and see what kind of population you end up and what kind of cancer incidence you can get. So this is kind of just a rule-based sort of methodology and what that could kind of look like as well. So something I want to talk about, which is something very recent that we've been looking in our team, is actually bias analysis and looking at this sort of equality of opportunity as well. So in terms of the bias analysis, we wanted to analyse the model for bias, and we decided to look at 4 different demographics features that we had. So this was looking at gender, deprivation levels, ethnicity, and also age. So here I've actually shown a graph for just gender, just because it's a bit easier with the 2 split. And as you can see, that actually in our model, the sensitivity for males is a lot higher compared to females, which is showing that males are being overdiagnosed from our model. Whereas the specificity is a lot higher for females and less so for males, which means even though less females are being diagnosed from a model, it's probably being more specific. It's actually identifying it more correctly. So we wanted to kind of look into this a little bit further. What we found is actually with the lift curve, if you start to increase those thresholds, what you can end up getting is a bit of a disproportionate change in your demographics and what's being presented at the higher level. So, for example, we were finding that more males were being in those higher risk cohorts because obviously the model was saying, okay, we're going to put more males. And that's due to the fact that in bladder cancer, 2/3 of males are more likely to be diagnosed compared to 1/3 of females. However, what was happening is it was being more than 2/3 and less than 1/3 for females. So it was causing it to be a bit disproportionate. So we ended up using this approach called equality of opportunity. So instead of looking at risk thresholds, we were more ensuring that the proportions were consistent as we sort of increased, decreased the smaller population we were looking at, but increasing the cancer incidence and making sure our demographics were proportional to what we would expect in bladder cancer. So this was kind of, how can we use our bias analysis and try and look at these high-risk cohorts, but ensuring that there is an equality of opportunity. And this was mainly only looking at gender, age, and ethnicity. Part of the reason deprivation went off of this is because when we did that sensitivity and specificity analysis, it was less having a bigger effect compared to these. And once you start going into the smaller stratas, it gets quite hard to manage your proportions. So we decided to focus mostly on these variables. So that is the end of the presentation. Thank you very much. I think I have quite a lot of time for questions, so yes.
Thank you very much. So the first of the questions is, can you tell us about the relationship between the size of the training set versus the size of the validation set? Is this a best practice ratio?
So I think there is variation in the literature of what you could use. I think 60%, 20%, 20% for the large data set that we have is actually quite reasonable, and that's partly because of how that undersampled works and how we then have to ensure we get out enough of that, like your specific cancer population, to do that undersampled training. So you do have to ensure you have quite a large amount there. We also wanted to make sure that when we so in terms of training, testing, and validating, what's really good about using your validation data set is you get out that area under the curve when you're doing that hyper-optimization process. And what you want to ensure is that when you then put that on the test data set, which is unseen, you want those metrics that are coming out to be like similar, because otherwise if it's going a bit higher, so if your validation is higher for your optimization and then it's lower for your tests, it would actually be a sign of overfitting. So it is a good practice to at least do these sort of splits, because it allows you to then get a bit more of an insight of how your model is actually performing.
Have you considered building primary care data into this, or would that make the scope too large?
No, we have definitely considered that. Unfortunately, we don't have access to primary care data within NHS England, although hopefully at some point we will. However, we have got access to something called the Leeds Data Mart, and we've currently got someone, actually Mary is in the room, but we've currently got someone that's actually trying to see if we can apply this methodology and extract out primary care features, obviously only on the Leeds area, but at least then we can get an idea of actually, by adding primary care data, how much does this actually add into the model, what extra features are we getting out, and would this be beneficial to apply?
Did you consider using oversampling rather than undersampling, and what made you opt for undersampling?
So I wasn't, unfortunately, in the team when a lot of that process went on. However, it was considered. And I unfortunately don't know the ins and outs of why we decided to go with undersampling, besides the fact that I think it definitely performed better from when they were doing it, in terms of the overfitting premise that I was talking about. But however, I don't know completely the ins and outs of that, unfortunately.
How do you ensure that biases in the underlying data didn't come through to your model?
We did actually do a lot of descriptive statistic analysis between each of our data splits, for example, to ensure that when we did do that data split, that there wasn't a significant difference between a lot of our demographics within the data. So that was to ensure that there wasn't going to then be a bias because you've got more representation in one data set via another, from when you're training to then validating to then testing. And then I guess in terms of what we then considered with a lot of this bias analysis was sort of just to evaluate that. I think the thing is with machine learning models, they are going to learn off the features, they are going to put more weights on stuff, and it is just about how do we combat that and how do we ensure that actually with these insights, how can we actually use that and derive that?
And there's a couple of questions on how the model's intended to be used, what's it being used for at the moment, and what are the plans for in the future?
Yes, so we're not currently using the models as of yet. However, we are speaking with the cancer program and talking more in terms of like how can we use this for case finding. This is still an exploratory project, and I think there's still a lot more direction we can go into. But the fact that we sort of have that link with the cancer program and we can sort of have these continuous conversations about actually in what direction can we do this and how can we improve this. There's definitely still more to go, but it's definitely good. It's a good sign that, for example, the top features were coming out and looking at this bias analysis, it's definitely going in a good direction.
Great. Thank you very much indeed. There are still further questions for you on the Slack. If you'd
Go on
like to go
Slack,
over there and answer them.
Thank you very much.
Next, we're going to be hearing from Simon Newey, who I know is here because he's been very active in the Slack channel. So Simon's presenting today on The Patient Does Not Exist, generating synthetic patient data with Wasserstein GAN.
Okay, thank you. So, in terms of the scope of this talk, towards the end, I will get to some relatively technical bits, which I'm probably not going to have time for, realistically. But if you're interested in that, please come and talk to me afterwards. So I'm going to focus the talk on what we did, what we achieved, and how it worked, but very keen to have those other conversations if you're interested. So I'm a data scientist at a medium-sized acute trust based in Doncaster. I've been there for about 3 years. We did some, and I'm going to talk about some work we've done around generating synthetic tabular patient data. So, there we go. I'm going to tell you about a patient who was lying in a bed at Doncaster in August 2022, aged 76, married, from a relatively deprived area, male, low news score, so low clinical acuity, had been in for 14 hours in the last year, hadn't attended ED or had any emergency admissions, was on an ophthalmology waiting list, periodically came in for dialysis, was at that time under the care of a diabetic medicine consultant and on a diabetic medicine ward, marked as not fit for discharge, with a red flag on their manual handling assessment and amber on falls and confusion, and was in fact marked as fit for discharge 24 hours later and discharged 76 hours later. And the reason why I can tell you all of this, and it is not a major data breach that I would be in a lot of trouble for, is that it is all made up data. So that is what I'm going to talk about, and the ways in which this data is made up in a way that is actually useful. So I'm sure you've come across the concept of synthetic data before, and there are a couple of different types of synthetic data, and it can be a bit confusing to understand what people are meaning when they use the word. So both types of synthetic data have their uses. In the left-hand column, I've given a summary of synthetic data that is randomized at a feature level. So feature columns contain values which are randomly selected from real data, say. There are various slightly more sophisticated ways of doing that. And those are great for giving a sense of the kinds of data in particular columns. Things like that, which can be useful for people developing early stage models for working with your data. It's very computationally cheap to do. On the other hand, there is another type of synthetic data which is quite a lot more difficult to generate and quite a lot more interesting, I think, which is synthetic data where you are able to retain the correlations between columns within your data sets. So, for example, it is not coincidence that in the case we just saw, the patient was both under the care of a diabetic medicine consultant and on a ward that specializes in diabetic medicine. That isn't guaranteed, but is a lot more likely because that's what you see in our real patient data. It's a lot more computationally expensive to do this, but it does mean that shared data can then be used for early stage machine learning development and analysis, which isn't possible if you have simpler data with independent features. So, as I just alluded to, the kind of case where synthetic data becomes extremely useful is when you want to share data. As we all know, there are an awful lot of rules around the data that you can and cannot share. It becomes very easy to share otherwise extremely sensitive data if what you're sharing is made up. There are a couple of caveats to that, but it's at least a lot easier. In our case, we were participating in a hackathon that happened last May. I expect some of the people here were involved in it. In fact, I know they were. Organized by Google and NHSE in collaboration. Discussing with the team who were attending this, who were taking part from our trust, there was a real appetite to focus on understanding patient discharge and how we could support that process. We had clinicians as part of the team, and their attitude was very much that this was the biggest challenge facing acute healthcare, and if we were going to do something blue sky at a hackathon, that was what they wanted to focus on. Unfortunately, the platform used for the hackathon we did not have security agreements with, so we couldn't put any identifiable patient data on that platform. And foolishly, probably, I suggested that I might be able to come up with synthetic data based on our real patient data that we would be able to use for this purpose. I'd read some papers about it. I'd done a bit of playing around with ideas. I wasn't altogether prepared for how complicated it was, but we were able to produce something that worked effectively, that we were able to take and use for model development in the hackathon, and I think to our slight surprise, we even won an award at the hackathon. And there is a photo of our team. I just thought I'd mention them. They're not here today. So the way in which we generated this data was using a generative adversarial network, or GAN. You may know a little bit about them. You may have seen an explanatory diagram a bit like this, which is one I just grabbed from Google. I don't claim credit for it. And in fact, this diagram is talking about images because this is the type of synthetic generation model used in image generation. If you ask an AI to give you an image of a parrot, this is how it will be doing it. And one of the things you can see in the fact that it's able to do that is it's very good at allowing for feature correlation. If the different pixels of the parrot weren't being correlated with each other in actually really incredibly complicated ways, then you'd just get a load of nonsense. Patient data fundamentally is an awful lot simpler than a picture of a parrot. There is no technical reason why this modeling approach can't be used to generate this kind of synthetic data. So in terms of how this model works, it's actually two semi-separate models. There's a generator, which takes in basically some random numbers and spits out something it thinks might look like your real data. And there's a discriminator, which basically is given things that are your real data and what your generator has come up with, and it has the job of knowing that whatever the generator has said is wrong and identifying the real data. As you run this, progressively the discriminator learns your data directly and your generator learns the features that would be needed to be plausible members of your data set indirectly. Very importantly, from a data protection point of view, the generator, the thing that's going to generate your synthetic data, never sees your starting data. There is no way, unless you have really overfitted your model in a quite difficult way to do, that you could pass real data through this accidentally. So I'll go into some of the difficulties we had in implementing that at the end, but before I get to that, it seemed worth giving an idea of what we were able to achieve with this kind of approach. On the left-hand side here, you can see a correlation heat map with different features we put into our model, for the real data. And you can see, for example, that the longer a patient had been in hospital, the days since admission, was positively correlated to being marked as fit for discharge. I'm not going to go through what all of these columns mean. Talk to me later if you're interested. But the important thing is that, as you can see, the two heat maps are pretty similar, not perfectly matching as you would expect, but show a strong similarity, so the correlations we want that will allow us to build predictive models are being passed through. And another way of visualizing this quickly, you can see some distributions. It's probably a bit hard to see. It's smaller than I thought it would be. But in blue, you have real data. In orange, you have synthetic data. Roughly, the distributions match in terms of how they correlate against each other. There are some mismatches. I think the model could have been better. So, the way we did this was to build a GAN basically from scratch using TensorFlow. The model itself was built very much using the functional API within the Keras module of TensorFlow. I would just recommend, it took me a while to find the functional API, but everything is better if you use the functional API. If you've used TensorFlow, I'd really recommend you take a look at it. Raw TensorFlow was used for issues relating to the loss function, which, again, feel free to talk to me about afterwards. The infrastructure we used to build this, we had one virtual server with specs pretty similar to a standard laptop and no GPU. So our compute for this kind of problem was really pretty limited. We did have to run it for sort of up to a week with regular snapshots taken so that we could recover things if something crashed, which it did occasionally. But yes, we were able to deliver this on quite modest hardware, which again gets to the this is something that is achievable point. And the performance was good when we were looking at a couple of 100 columns. Towards the end, when we were trying to get in the whole of a patient's history in a more dramatic way, we were getting up to the thousands of columns, and we had the choice between training times becoming unworkable or the quality of the model deteriorating. So that was where we got stuck. So very quickly, 3 tips for if you are planning to do this yourself. The first, if you want to build a GAN, is use a Wasserstein GAN. Google it. I'm not going to explain it. It's confusing. Very roughly, you don't want your discriminator to just be telling you whether the fake data is real or fake, because it's generally pretty easy for it to go, no, that's fake. And then your generator gets discouraged because everything it suggests is just told that's fake, and it stops learning. And yes, there's a paper that was very useful in pointing me to how to do this, which looks at basically this problem and has some interesting insights if you're wanting to get into that. The second thing, which goes for an awful lot of other work if you're wanting to do anything with neural networks, is use the right activation functions. So you've got lots of different data types in a data set like this. We were only working with tabular data, but you've still got linear, Boolean, and one-hot sets of data. These need different activation functions in their output layers, and the important thing, the important tip, is you can put different activation functions on different parts of your output layer if you have multiple output layers, which again is really easy to do with the functional API in Keras. Last one is to use a wide discriminator. This was where we really started to hit limitations. For most neural networks, you don't use wide neural networks because there's no point. The issue here is that you need your discriminator to not forget the old patterns it spotted in your generator. You can have a situation where, like, your generator goes, okay, we'll try thing A to try and fool this. Your discriminator learns not thing A. Your generator goes, okay, thing B. And then in the process of learning thing B, your discriminator forgets about thing A, and your generator then swaps back to thing A. And they just chase each other back and forth, and you stop learning. The way you deal with this is to have enough redundancy in the size, the width of your discriminator that you can allow for that kind of memory. Okay. Thank you, and please pick things up with me afterwards.
Thank you very much indeed. That is perfectly to time. So I'm just going to ask one really quick question, which is, do you think that your model could be used by other trusts, or is the model very specific to the people of Doncaster and Bassett's Law?
Something similar could be built. The same model perfectly, it was actually, yeah. You could build a similar model for another trust. Ours was trained on our data. It knows about our wards. As such, no, you couldn't just copy and paste it. But if people are wanting to, then talk to me. Thank you.
Thank you very much. Do we have Elias and James?
Yes.
Fantastic. This is Elias Altrabsheh. Am I pronouncing that right?
I'll pronounce it in a second.
Okay. And James Sibbit, who are going to be speaking on the topic of streamlining machine learning development at the NHS via open source tools.
Hello, good afternoon. First of all, I'd like to thank everyone here, the coordinators, for hosting such a great event. It seems like a great community, yeah, the talks have been great so far. As well, I think we are one of the only talks where there's two of us here, so hopefully we'll keep it to the time, and because I know everyone's very eager for lunch after us. In terms of, I guess, the talk, so the motivation here is really from, I come across there's a particular machine learning model in the area of radiology, and I was listening in terms of the development of this tool, and it took them around 500 iterations in order to have this model into production. So obviously, if you're doing this in a manual process setting, this is going to take you a long time, and it's going to cost you a lot of money. So just to introduce ourselves, my name is Elias Altrabsheh, and I'm here with my colleague James Sibbit, and we are from a company called Define. We are a consultancy who work on topics around AI, machine learning, data, and software across multiple industries. So we've come here to bring sort of, our knowledge in terms of, how do you actually operationalize and productionalize machine learning in a larger scale. So I just want to start off. So this is where, to start off here, I want to go through some of the challenges of what we see. And these are challenges you might be currently aware of in the NHS. So one of the top ones is, we're all aware that NHS is a system as a whole, but in terms of the data, it's very fragmented. There's around 90,000 data flows running through the NHS across 7,000 data providers. So there's a lot of data there. There's fragmentation. And if you think about building a system on scale, this is problematic. It's a bit of a challenge, which is particularly around the infrastructure in terms of how to develop these models on scale. Another particular one is I want to talk about from an organizational perspective. Obviously, there's a lot of elements from an organizational perspective, but we tend to see, I guess, a challenge in terms of getting the right people doing the right things. And in terms of the elements of operation and monitoring such models, you need to have a certain skill set in order to achieve this goal. Data quality also seems to be quite a bit of an issue, and for those of you who are data scientists, you might be aware of this. There's currently around, I think some figure I found, there's around 200 million unstructured data documents with 1 trillion structured data rows currently within the hospitals. So these are across data silos. And of course, in terms of this, the NHS, because it's one of the biggest, largest organizations generating data, in terms of monitoring the quality of the data, this probably does not exist into a standard where the quality of this data is ready to go to build these particular models. There's also an aspect of validation, and you might be aware of this in terms of the different trusts, the standards and requirements needed in order to have your model applied on scale. I wanted to take a moment, and this is probably comes also from our experience in other industries. Generally, so machine learning models in reality, well, some of them fail. There is some latest figures, I think, which is around 95% of machine learning projects fail in the clinical setting. So this is a figure from the US. I'm not sure if it's the same here in the UK, but I just wanted to highlight what are some of the primary reasons for these failures. And if we look at here on the left-hand side, there's technology, fragility, and scoping and planning sort of take most of the reasons. And now I want to introduce this concept of, well, how do you operationalize this thing? And this concept called ML Ops. And on the right-hand side, there is some of the elements which ML Ops tries to solve. So I'm not going to mention all of them due to time, but one of the ones which I just want to highlight. So they're highlighted here in orange, and I just want to focus on sort of data drift as one of them, as well as the infrastructure and stability needed. So to go to my next slide, I think before we go forward, it's probably a good idea to define what we mean by productive machine learning. And there isn't one definition. This is a definition I see as potentially fits, and a productive machine learning system effectively solves a real-world problem. It may solve this by recommending decisions or actually performing decisions to solve a real-world problem. But this system as a whole, it has to be trusted. Else these decisions, no one is going to take any notice of them. And it has to be trusted in a way that it has some sort of explainability. It can be validated. So you've got some sort of tracking in terms of what are the versions of the models and tracking what data is actually going through. Lastly, it also needs to sort of manage evolving new data. So the topic I mentioned earlier around data drift, you want your machine learning system to be able to evolve based on new data coming through. And yeah, this seems to be actually quite of a problem in terms of performance of the models in healthcare tend to go down with time. So you want to have a system which has a robust monitoring setup. There's also two other aspects I just want to quickly mention is you want your system to be operational resilient. If you've got some sort of machine learning system in a triage, you want it to be responsive, you want it to be always available, so you want the person who's using that system ensuring that they can actually use it and the user is happy and it's going to be up and it can respond in an appropriate time. You also want your system to be integrated from a data perspective, but also from other systems perspective. So you want your system to integrate well into the other systems so you don't have, so if something went wrong, you don't have this downstream effect of other systems being affected. Now, what I want to have a look at here is just to make a point that when we talk about machine learning models, the model itself isn't the largest, it isn't the everything, it isn't the largest component of it. There's, from an end-to-end process, there's many other components which you need to take into consideration. And yeah, there's quite a lot there. And in order to really sort of automate this process and to have this in a sophisticated way, this is where this concept of MLOps sort of starts. And I just want to highlight here for the data scientists in the team. So a lot of us are familiar with this sort of data, so from the idea to the data collection, the data cleaning, the model perspective. But from the right-hand side, when we talk about operations and integrations, these are the areas which we're almost less familiar with. But in order to have an end-to-end cycle where you have a system which is robust and productive, as I gave the definition, the elements on the right are actually very important to have in play. And so I'm going to stop here with a sort of statement and say, okay, well, the classical data science workflow is not suitable for what I define as a productive ML model. And I guess what I'm trying to say here is we're probably all familiar when we start a data science project, you have this sort of experimental mindset in play where you can, this graph might be familiar in terms of some of the setups which you might have experienced, is you tend to have a dichotomy between the model and the operations. And this dichotomy causes some issues down the line if you want to have a productive system. So think about, you experimented in your notebook, you tend to have your sort of data dump, and you tend to train your model, and then which is separate to the actual operational stage in terms of production. So some of the issues which might occur here is, or some of the side effects is, you might tend to have your model and application code sort of in one place, which might cause some downstream effect of something breaking something else. But it's also the aspect of when you're in this experimental stage of training, you might not be tracking all of the versions you have in terms of the model. And this sort of, I guess causes some issues down the line. So thinking about this slide now, there must be a better approach on how to do this to achieve this productionalization state. And this is where I'm going to introduce my colleague James here to go through and tell us about this approach.
All right, thanks very much, Elias. Elias has been a little bit of a harbinger of doom thus so far, let's say. But we're going to good cop, bad cop it a bit, and I get a nice role of being the good cop here. So obviously, we've seen a lot of issues, right? We've seen a lot of issues which we're all familiar with. But Elias is right, there is a better way of doing this. And he's used the phrase a few times now, but let's formally introduce it. The way is MLOps. So before I introduce MLOps, I'm going to take a little step back to the dawn of time itself, if the dawn of time was about 20 years ago, and introduce the concept of DevOps, which I think a lot of people are probably familiar with. It's the intersection of development and IT operations, right? To iteratively integrate and deploy your code. With this, on the right-hand side, we see an iterative process, right? You're writing your code, you're packaging it, you're deploying it to various environments, you know, your development, your UAT, and your production environments. And then you're monitoring that code, and you're using that monitoring to feed back into iterating on your code and improving it. We can take a similar concept and apply it to the machine learning lifecycle. And thus we get the concept of MLOps, right? So there's multiple places in the machine learning lifecycle, from development to, you know, model iteration to model serving, where we can apply this iterative approach of DevOps to those particular aspects. So for example, we can version our model, we can track experiments on our model and use that to feed into actually developing the model further. And we can do, you know, retraining on productive data, all of those kind of aspects. So what that gives us is hopefully a slightly less fragmented view on the machine learning lifecycle, and hopefully something that's a bit more unified that we can work with. So before I move forward, I'm actually just going to go back. Let's again reiterate what the issues we see on this slide are. So we've got segmented exploration on the model up there, which eventually we get a trained model out of. Then we're shoehorning our application code and our trained model into one registry, deploying that all in the same place. It makes iterative deployments difficult, and the operations are really separated. So skipping forwards, if we apply some iterative MLOps thinking, hopefully we get a bit of a nicer picture. So what's the difference in this slide to the previous one? Well, I think one of the main things I want to highlight is the experimentation pipeline. So up at the top, we've got our machine learning experiments, where we really carry out our exploration, but the difference is we're tracking these experiments, right? We're taking the outcomes that we see, and we're formally monitoring metrics so we can use them to feed into the model development. I think, thinking back to Nick's presentation earlier, she had that really nice sentence where that bloke was sitting at the desk saying, "Changed my mind about that statement about reproducible analytics." Reproducibility and explainability in machine learning concepts is vital, really. And if we track our experiments, everything becomes reproducible instead of it just being one trained model we get out at the end. Now, once we've tracked our experiments, once we've got a model we're happy with, we can deploy it into a registry, and then that can be trained down in the bottom pipeline. And that trained model we can serve up separately to our application code, right? So we can serve it up with an API. What this means is we can iterate on our application code, the thing that's accessing our scoring endpoints for our machine learning model, and the actual model itself. We can iterate on them separately. And what that allows us to do is have an iterative deployment process for the model. So let's say we're monitoring the model performance in production, and we see it's flagging. Or maybe we get some new productive data, we get another training data set. Then what we can do in an MLOps concept is we can trigger re-execution of hyperparameter tuning, we can trigger more training, and basically feed that back into the model training to then iteratively deploy new versions of that model. And in an MLOps world, all of those models are versioned, they're tracked, all of that good stuff that we like. So we can see how MLOps sort of improves the target picture, but we still don't really know quite what it is, what it entails. So let's break it down. MLOps is, it's a way of thinking, but it is also actionable, tools and processes that you can use in your day-to-day workflow with machine learning that sort of improve the workflow. And what we're looking for is an end-to-end iterative pipeline of your machine learning lifecycle that gets you to a point where you can continue to iterate with your models. So, I mean, this is no surprise to anyone. It all starts with development. So when you're developing your model, we're looking for collaboration, right? We're looking for a place where multiple developers can come in and work on the same model. I mean, we can use tools like Git, we can use collaborative IDEs to do that sort of thing, but it all starts at development. Now, in the picture we saw before, this development might happen on, you know, a laptop, and then the training might also happen on that laptop, and then the model might be taken from that laptop and put into production. Where we want to switch things up a little bit here is once we've developed the model, we want to push that via a pipeline to a place where that model can then be trained and experiments can be tracked centrally, so we improve collaboration, right? So the next step in the machine learning operation pipeline is pipelines. So yeah, these are a series of you know, pre-processing steps, basically using continuous integration and continuous deployment practices to deploy the model to somewhere where we can train it centrally. We also want to version the model. So in order to improve reproducibility, we basically want to track all of the changes we make to data sets, to models, all of that kind of stuff, so we can always go back to a previous version of the model. And you know, if we've been using that productively, then we can go back and use that previous model. And once we've versioned our model, we can jump into training it. This training can obviously happen, it could happen locally with GPUs, it could happen in the cloud, it can happen wherever you want it to really, but the main thing that we want to enable here is tracking the outputs of these training runs. So that comes into the next stage, which is experiment tracking. And this is what makes your results reproducible, right? If we monitor our training runs and we get metrics out of those training runs that we can then attach to a version of the model, then we get a really nice amount of visibility over the entire end-to-end model. Once we've trained our model and we're ready to actually use it in production or lower environments, we want to deploy our model, and we can do that via containerizing it and deploying it somewhere on potentially a cloud platform. And we serve that model up in production, which we can likely hit with APIs. Now, one really crucial facet of the MLOps lifecycle is that we don't just want this to end once we get to serving the model. We want to actually be able to monitor that model in production. And then using that monitoring, we want to be able to track performance, you know, track metrics surrounding the model. So if there is new data that comes in, like I mentioned before, or, you know, model metrics start to lag, model performance starts to lag, then we can think about going back in the life cycle to retrain the model. And that's where it becomes an iterative process. Okay, so hopefully we've got a bit more of an idea of the end-to-end MLOps lifecycle now. How do we implement the thing? Well, the good and bad answer is that there's loads and loads of ways you can do this, and in some ways it's quite overwhelming. Now, for every stage in the life cycle, you have different ways you can implement it. You can implement single stages of this life cycle independently to the others. Obviously, the most benefit is if you implement the full thing, but you can implement individual stages, and for each individual stage, there are both open source tools and commercial tools we can use, but obviously we're all here for one reason, is to talk about open source. So let's focus on that. I'm not going to spend too much time on the slide because I think we all already know what the benefit of open source versus commercial is. But especially in this space, when you're using these open source tools, the real pros you get are that it makes your procurement easier, right? The tools we want to use here, you can essentially use in any context really, and you only need to implement them around certain parts of the life cycle. So it's a quick way for a smaller team who's experimenting with a model to potentially leverage parts of the pipeline quite easily. There are obviously lots of commercial solutions available, which, you know, do offer a lot of support and stability, but naturally you have vendor lock-in, you need procurement to actually be able to utilize those tools, and there's some issues. So yeah, the last thing I want to do is highlight something I think Scarlett mentioned earlier that she was using in her work, a tool called MLflow. So MLflow is an open source solution, which was, originally it was developed by Databricks. There is a commercial version that is provided by Databricks, but more importantly, there's an open source version that's incredibly easy to download and use. And it covers a few aspects of the MLOps lifecycle. In my opinion, it covers the most important aspect, which is the tracking. So it's really easy to set up around your model training, so you get auto logging on your metrics when you're training a model, and basically a continuous feedback loop on how that model's developing. So I've got this set up on my laptop. We did debate doing a live demo of this, but decided we didn't really have time. But if you do want to see it, I'm sat over there, so you can come and have a chat. But in the bottom right, we've got a screenshot of the tracking UI. I've just set up a pretty simple random forest regressor on my local machine. And all I'm doing is repeatedly running that regressor with different estimators. But you can see in the bottom right, every single training run you do is tracked, and you get a bunch of metrics out of the end, which basically gives you a really nice way to see how your model's developing over time. MLflow will also help you with the versioning of your model, so packaging up your model, essentially giving you a way to track the progress of your model there. But yeah, the tracking, in my opinion, is the really powerful bit. So I think I'll wrap it up there. Just to summarize, MLOps, I think, is a really powerful way of thinking. You know, it is an organizational framework that you can use to think about, I'm starting to develop a new machine learning model. How do I take it from my laptop to production? And it's a really nice way of organizing that in your brain, but there are also some very tangible, easy to download tools like MLflow that you can use in your day-to-day work to basically make everything a bit easier for yourself. Cracking, okay, I guess, any questions? Yeah.
So yes, indeed, we have questions from the Slack channel. One of the key challenges for machine learning implementation in healthcare, and for elsewhere for that matter, is the black box nature of many machine learning techniques, hence the increasing focus on explainable AI techniques. Does your pipeline consider these aspects?
So explainable AI in itself is a whole world of something we could talk about, obviously. You could put, explainable AI techniques into this pipeline. Again, think about this pipeline as a way to organize the steps of how you're developing your machine learning model. And for me, I put it into the tracking part, right? So you're developing your model, and there are ways to improve the explainability of your model. Lots of different things, of which my brain is forgetting all of them immediately. But essentially, I would view that as a place when you're training your model, you can incorporate explainable AI methods into that, and then keep track of them, right? Keep track of the metrics you get out when you're testing your model, and then you've got a track record of those metrics. So, yeah.
If you're iteratively training the model with new data, how do you avoid overfitting to that data and ensure that the model still works well for future data?
That's a good question. I guess that comes down to a data quality question. So this iterative training, it wouldn't be a case of you would do a training run and then it would just get arbitrarily deployed to production, right? You would do a training run, you would have all of your validation on top of that. You would see how the model performs on this new data, and you would treat it as, okay, does this model achieve the result I'm trying to get it to achieve? And if yes, then I can deploy it to production. This isn't a complete hands-off, I just let this machine run and we see where we go. There is still, human intervention there, and we still use our brains to make sure we're addressing the problem we're trying to address. But yeah, overfitting data is always an issue that you need to think about, but you'll still be thinking about it in this context. You just have more tools to help you, analyze that issue.
Fantastic. Thank you very much again. And next up with a very short presentation, we've got Ella Kaye for the final couple of minutes before lunch. So this is Ella Kaye with a community talk on rainbowR.
Hello, and thank you very much for squeezing me in today. I'm Ella. I'm here to talk to you about rainbowR, a community for LGBTQ+ folk who code in R. It's a very short talk, but everything I talk about today and all the links on these slides you can find from rainbowR.org. No? Okay. Okay, I'm going to need to figure out how I can advance my slides. Is there? There we go. Hey, okay. So in our very short time today, I'd like you to know that and why we exist as a community, some of what we do, and how you can get involved. So our mission as a community is to connect, support, and promote LGBTQ+ people in the R community, and to spread awareness of LGBTQ+ issues through data-driven activism. But how do we do that? Well, in two parts, really. So on the connect, support, and promote part, a couple of initiatives. We run monthly online meetups over Zoom. The next one is going to be on December the 4th. And in these meetups, there's a chance to chat with other community members, mostly about R. We also run a buddy scheme, and the way this works is once every 3 months we open up a form where if you want to be paired with a buddy in the community, you fill in the form, and then we run an R script that reads in those form responses, randomly assigns buddy pairs, and automatically generates and sends emails introducing each buddy pair alongside some ideas to help get that conversation started. On the data-driven activism side, we host a repo on GitHub, Tidy Rainbow, of LGBTQ+ data sets, which are free to use for like Tidy Tuesday style analysis and visualization, or to use in examples and blog posts and teaching, those kind of things. We're always looking for more data sets, so if you have any, importantly, ones that you can share, please do let me know. We also recently launched a book club where we are discussing the book Queer Data, using gender, sex, and sexuality data for action. We had our introductory meeting last week, but the book club is still open for anyone to join as we discuss the chapters over the coming months. So if you would like to get involved, there are various ways to do that. Go to rainbowR.org/join to fill in a form to join our community. If you do that, I'll send you a personalized welcome email to the community. You'll get an invitation to join our Slack group and an opportunity to sign up to our newsletter. We're also on Mastodon and Blue Sky, also LinkedIn, and there's an email address as well. So, if you're LGBTQ+, and you would like to join a vibrant and supportive community of fellow R enthusiasts, or if you're somebody who would like to support and promote LGBTQ+ people and issues in the R community and beyond, please do go to rainbowR.org to find out more. I look forward to meeting you. Also, I have lovely stickers. And I'm very happy to take questions now, but if we're short on time, also to chat to people over lunch.
Fantastic. Thank you very much indeed. Yes, as everybody I'm sure is keen to hear, it is now lunchtime. We will reconvene again at 1:55 to 2. If anybody is interested in signing up for the socials, then that's happening at the back of the room. There are also stickers there, I believe.
Mm-hmm. Did Zoe want to say something about the Uncom?
Yes.
Yeah. Also.
I have a microphone. Right. This is going to be 30 seconds. I'm standing between you and the lunch. Uncomfortable place to be. Many of you have been last year here at the unconference part of the conference. You will see where the food is. There's an empty timetable for tomorrow. So essentially we're going to have 3 tables in a corner discussing stuff. This is how you can suggest a topic. You grab a piece of paper, you write a title, and you write who you are. And people will start sticking stickers. I'm interested, I'm gonna come. Or, this is cute, but I can't come because I'm actually here watching or presenting something else. As you're having a lunch, have a wee wonder, have a wee read. Do come and do enjoy this tomorrow. Last year was super fun. So, thank you. I'm Paweł, and this is gonna be Unconference tomorrow. Lunch?